All right. So yeah, I'll just start off slowly. For this presentation, I'll go a lot more into detail with the project we did ourselves last year. And yeah, I would love to talk about the phases of the project and actually spend most time of what we learned during the project, because a large part of the project is a learning project for us, but also we hope for the rest of the industry. So we have decided from the beginning to be very open about our development and share a lot of key facts of, for instance, our material recipes are completely open and everything, because we hope to get a lot of feedback from the industry and from other people who wants to try it. So yeah, so the background of the project, we started, as I just told before, we had the 2-year research project that was made along with NCC and 2 other Danish companies. Or that was, you can say, that is the way we went into this field. Then, after a conference we had last year in February in Denmark, we realized that actually no one had built a house in Europe at that point, which was lived up to European standards. So, as a startup company we just thought, let's do it. We had no background in construction and no idea how to build a house, but we thought we could do it. So that was the starting point. That was in March last year. And we soon found an architect, Anna Goidia, she actually was here last year and talked about the design phase and so of the project. She was quite newly graduated from CETA Institute in Copenhagen. She knew a lot about 3D printing, and she was obviously an architect, so we thought that was a good match. And she created this beauty. So it was, I think she told a lot about design process. I'm not very much into that part, but I've been within the construction of it. So how do we 3D print a house? As I said before, when we 3D print a house, we're actually only talking about a sub part of the house, so the raw walls of the house we actually 3D print in. So the building process, if you look at the first 3 steps, is completely regular. You'll see some excavating, digging for the slab foundation, some reinforcement, some casting of concrete. Actually, we had a very bad soil out in the area, so we had to do piling as well for the house. So all of these parts done without a 3D printer. Then we have the erection of the printer on site. So that means that on this plate foundation we built the printer and printed the slab. And the reason we had to print on the top of the foundation, actually, this shell you'll see here, that's 3D printed, is because this was the first time we met the interface of the normal industry. So we had a very, very tough time communicating because obviously the top of the foundation should match the house, the shape. But we had a very difficult time communicating this shape to the normal concrete people, because we said we want this house, so we need the top of the foundation to look like this. And then they're like, we don't know how to do that. And so there we hit the first problem. So we ended up printing this part. It wasn't supposed to be like that, and then afterwards they filled up the printed shell you can see here with insulation. So this is polystyrene insulation. They filled it up with you can see these here are the pillars for the columns later to be cast out. You'll see electricity, plumbing, etc. Everything is put into here. So that is, again, we printed this part, and then the conventional industry people came back and filled it out with the normal things. After that was done, we created the house. So that means we printed the outer and the inner wall with the printer. And as I write here, it's 50 hours, 55 hours of printing time. But they were spread over a month and a half, because we had quite a few of issues. I'll come back to those later. Afterwards, we filled out you can see here, this the inner wall, the outer wall here. This is a column. So we casted out the columns here with concrete and reinforced steel. Then we filled out the space here with insulation. This is paper granulate insulation. Then again, the roof is made as a wooden construction here, and windows and doors are inserted. And we have painted the walls, put in flooring, what's it called, like smoothed the walls and so on, some of the places, and put in furniture, etc. So, and from the outer you can see the coating, painting, like everything is finished. And some points we have added the like trial application of bricks because it's an experimental project, so we want to just have a go. What can we put brick on top? It's these thin shell bricks, stuff like that, because we want to be able to see what is actually a viable way of 3D printing houses. What makes sense also in a business perspective, because obviously we are business, so we also need to make money and we need to survive into the future. So yeah, and hopefully this will begin soon. Maybe. The video. Maybe I have to push. Here we go. So here you can actually see the process going on. So maybe I'll just pause it. Maybe I won't. Oh, shit. Here. All right. So if we look at this this image here, so as you can see, we print layer by layer by layer, roughly 20 millimeters layers of concrete, 50 millimeters wide, both the inner and outer wall. And as you can see here, we have all the columns. So what we print is actually just a hollow space for the columns to later be cast out. In the bottom, we had reinforcement steel going all the way down to the foundation. And after we are done, we put in further steel up to the top and cast out. You can see in the back here, that's actually me, mixing materials batch by batch. So that is because I'll be back on that later, but because it's everything apart from the printing was very manual. And as I said, also that we are completely new to construction, so there's a lot of these things that we had never done before. So we just like did what we thought was the most efficient way to do it. It probably wasn't. But in the back here, you'll see a lot of material, and you'll see a guy over here who's actually sieving all that material, because during the process, when we actually was like 20 meters up into the house, there was this. You can actually see some of the spurs of the explosion here. This hose here exploded because we had some large rocks in the mixture. We ordered the mixture to be a maximum of 8 millimeters stones. We knew we could handle that with all our gear and pumps and so on. But by some error, I don't really know where it happened, we had like these like 20, 30 millimeter stones. So they came into the pumps and into the hoses and clogged the whole thing, and stuff exploded. But obviously that delayed, I think that explosion delayed the project by 3 weeks, because then we had to like go back, fix everything, get a new pump, get a new extruder, get a new hose. Then we had to find some mechanism which could sieve all that material, because we had like 15 tons of material here. We couldn't get it out of the tent because we didn't have the room to put in a truck. So we had to like sieve it in place and hire a guy to just sieve material from morning to evening for the rest of the project. So yeah, that was one of the learning points here. Over here, we have Michael, my colleague, who is, it's a bit hard to see, he has like 2 computers. One is controlling the machine. The other one is connected to some cameras mounted on top of the extruder here. So he at every point of the process can actually see what is going on directly where we are printing, and then adjust accordingly. Because it was the first time we did this, and because we mixed it manually, there was like variations all the time, small variations in material and so on. So it meant that for instance, the wall would be a bit more rough one place, or suddenly it was like a high moisture in the environment, and the concrete became a bit softer, and it floated faster out of the nozzle. So we get like this hanging things, and he needed to like adjust for that right away in the machine. So for this process, he was like there all the time, like pushing 2 buttons, like extrude a little bit more, a little bit less, a little bit more, a little bit less, for the entire day. So as you can see here, 3 people working full time to have a machine 3D printing house. Not very efficient, and that's also going back to the point from before that we are not really world champions in this industry yet, and nobody is, because if you look at all the videos from all the others, you have like 10 guys around a 3D printer doing a house. And that's all right, because all these 10 guys need to learn something in order for it to be better and improve on the technology and so on in the future. But let's see if we can continue this. All right. Yeah, so we continued. You can see it's night and day, night and day, night and day, and at some point the camera can't really see, so we shift the angle. Actually, here you can see a little bit better over there. The mixing station, the pump goes through, and here. Scaffold going around, because we had to put in wall ties all around in order for the walls not to topple over. And actually, if we go a little bit back here, it's actually good to see. You can see here, these splits here, roughly, are what we could print in one day. So this is roughly 50 centimeters on a good day. So that is what we were able to do. That's 50 centimeters of the entire house, but that's 50 centimeters in roughly 8 hours of printing. So you can see there's some hours in this project. Obviously, the machine will be faster, and we can do it faster and so on in the future. But this is the reality right now. This is how we did it. No. Can we move beyond this? Yeah. All right. A little bit about the machine itself. It's a gantry printer, so as you can see, like 4 legs, very simple. 8 by 6 meters on site. We had 20% of recycled materials in the mixture. Tiles that were crushed down. It was actually because of the initial project was funded by a Danish grøn omstillingsfond. I don't know what it's called in English, but it's like a green sustainable so we were very focused on what could we do with recycled materials in this mixture. That added a lot of issues, but it was a good, you can say, a good experience, layer by layer. Roughly printing 6 meters per minute, like in the vertical direction. We believe soon we can print like 18 meters per minute, and then 50 meters per minute, and so on. So that will increase really fast. So we had a layer time of roughly 15 to 20 minutes, depending on the moisture in the air and the temperature and so on. So this time here actually becomes very important later for development, because when you look at the building and the material, because you need to design your material for the time. Because imagine that you have wet concrete, and then at some point, 15 minutes hopefully, after that you put on another layer of wet concrete. Then that layer, it needs to be hard enough to actually be able to hold its shape and hold its height, but it needs to be wet and soft enough to fuse completely together with the next layer added on top. So you have like a small sweet spot of a window, and that is depending on material, environment, printing speed, geometry, how your printer moves, vibration, a lot of things. So this exact material recipe was perfect for this exact house with this exact printer. It's not sure you can take it and build anything else with this exact recipe, but it was really good for this project. Yeah, so 1 meter is roughly 12 hours if you print continuously without errors. Yeah, so what did we learn for this? A lot, obviously, and there's a lot to learn still. We know that we haven't really scratched the surface of what we can do, and we really want to improve. That's also what I said in the beginning, that we really want to be open about. Right now, I can tell you everything, like every minor error we had, every software error, every hardware error, and where it happened and why it happened, or why we think it happened if we haven't tested it thoroughly yet. Because we want to learn. We think this technology is still very, very new. We want to get feedback. We want to have other people making experiences as well, so we can share the knowledge there. And then there's a statement of complexity is for free in 3D printing, and it is definitely for free, but not for the finishing, because we finished the printing in, I think, late October last year, the printing of the house, and last week we removed the tent, because then the roof was finally done. So that means because we have done this wavy, shapy shape, then everything else was really complicated. So have the roof company make a roof that fit that exact wave, and yeah, there was quite a few issues involved in that. So it's taken like, yeah, way too long, and you can see the price of the construction. Actually, the 3D printing part was quite cheap, but everything else was more expensive. So in terms of competitiveness in the market, we are really creating a lot of issues for ourselves by doing really crazy shapes right now. Obviously, there are solutions to those as well, but we just haven't found them yet. And we saw these 4 areas that is really important, and they should work together. So the software, the printing system, the material recipes, and the material handling. And I'll try to go through them bit by bit. So on the software side, obviously we have a machine out there, and all of you who've tried 3D printing with a small machine, you know it's a combination of how you draw in CAD and how you convert that into the machine code, and how your machine interpret that code, and then how you control the machine, and so on and so forth. And so what we thought, actually we started using normal software for small 3D printers because that's our background, that's what we know. And we soon figured out that that's really difficult when you scale it up, because you will see every little turn, every little shake, every little vibration can topple a wall or destroy a part of the house, or like it's very sensitive to small things. So we actually ended up building or writing our own software to control it instead, because then we had much more control of what was happening. But also, if we look in the future, then we know that BIM software will create most of the houses, or BIM-like software, Rhino or something like that. So we need to be able to interpret that in a more smart way than we are actually doing now. So we are looking, instead of polygon models that you usually use for 3D printing, we are using BIM input, so we can take a Revit input or something like that and put it directly into the printer and interpret it that way. Because we believe right now it's worse, but we believe in the future we need to do that in order to be able to move into the industry. And obviously, software needs to be easy to and usable to everyone. Right now, it's a lot of lines of code that only Michael can use. So at some point, we will need to make interfaces and something for other people to use. Printing system. There's really a lot of difference between the on-site and off-site printing. As I mentioned before, the environment, the temperature, if it rained the day before, we had all the material placed on the ground, so a lot of moisture would suck up, or draw up into the material. So if it was raining the day before and we printed, then we would need to adjust the mixture day by day. So we might add 200 milliliters less water to the batch, because otherwise it wouldn't work at all. So we are really vulnerable to the environment, to the system. We really needed a stable structure, because everything, as soon as it moves or vibrates or so on, we could actually topple down walls. But what we figured out is actually when we have it was a little bit by mistake, because at some point Michael sent the wrong code to the printer, so instead of moving up, it moved down. Unfortunately, it moved down into the thing we'd already printed the day before, which resulted in a 10 tons press in one point on the wall. Fortunately, nothing happened, but there was a nozzle breaking, but we printed a new one, so it wasn't a problem. But then we figured out that, okay, but we can actually use that in the future. We can take this and we can just install a measurement system. So we can go down, and after we have printed and let it dry, we could actually go down and pick, for every 20 centimeters of the wall, we can actually check the strength of the wall after we've printed it. So a lot of those thoughts came because of weird errors that happened during the print. Then we started thinking about what else can we actually put on here, and then we, instead of thinking of 3D printing, like the machine as a 3D printer, we actually started seeing it as it's just a positioning system, a very precise positioning system that you have on the building side. And then you can start adding, a printhead is one function, then you can have a painting gun, or you can have insulation, and you can just slowly start adding features to this movement system that you have. And then we went back and said, okay, the movement system, could actually be anything as well. It could be a robot arm, it could be a gantry, it could be a crane, it could be like a small robot. It has very many variations. So while we're doing, like you see this gantry printer, it might not look like that in 2 years or in 3 years or in 4 years, but it's just how it looks now because of coincidence, because that's the printer we know and know how to control right now. It should also be modular, because obviously not all houses are the same. Every house is, like most houses are different, are in different conditions. And we need a lot more precise control of everything that happens, everything in the material and so on. If you look at the material, oh, I need a picture there. If you look at the material specifically, if some of you want to experiment, I think it's on our website somewhere, or I can give it to you. It is based on concrete, or cement, sorry, sand, gravel, crushed tiles, fibers, polypropylene fibers, and a bit of plastifier to make it more fluid through the pump system. But the difference between what we did and what we see around is that we actually put in gravel and large grains, because what most recipes we see around are actually just really fine mortars. But if you look both at the price, but also at the performance, the strength performance and so on, you really want larger. You really want, at some point, you want stones in your concrete, because it adds a lot of strength, and it makes it much cheaper in the long run. Yeah, fibers is at this point necessary. I'm not sure in the future. It was the only solution we could get to avoid setting cracks. And then again, recipes are really vulnerable to small fluctuations in moisture, in water, in like so as little as 20 and 50 milliliters of difference in water. When we added it, it could mean like a really good print or a really bad print. So there's obviously a lot of issues there. So we think open source materials definitely is our way to go for the future, because we want not to be material experts. We want others to contribute with their knowledge as well, because again, we are not construction people. We are technology people. Yeah, it's actually quite easy to get bonding between layers, but it's yeah, controlled by layer time and setting time and so on. Flow characteristics are really difficult to get straight, especially when you're out in an environment that changes. I think it's easier inside a construction hall. Yeah. And if we look at all the recipes out there, as well as our own, there's a lot of cement being used. Like the percentage of cement is 15–20% higher than normal concrete you cast out there. Which means for the environment, even though we put in 20% of recycled materials and actually used less material in weight than you normally would use, then the high amount of cement is actually making it less environmental friendly, because the cement is a big sinner in concrete. It's the one that like it's needs a lot of heat to produce and so on and so on. So there's definitely way too much cement in this material. So we need to find either a non-cement binder to use. That is why I think this wood project here is really exciting. Or find other recipes that has a lower content of cement, where we can control the fluidity in another way. And yeah, we hope that some of the material guys out there will help us do that. And the material, oh, like this. The material handling system for this project was quite simple. As you can see, the sieve, that was the one we made to avoid all these big stones. Very basic mechanical thing, but required one man full time to do it. Obviously, we won't need it for the next project. I think we've learned how to control our material now. Concrete pump and mixer. We actually ended up detaching this part and only using the pump and another mixer, but that's a different story. Hose to supply the material, so you can see up here, just mounted in some wheels in the roof. We have the hose where we pump the material out to the printhead, and we have the pump here, or this part of the pump here. This was controlled just by a switch by Michael, so he was looking at the camera that looked down into the reservoir up here. So every time he's like, okay, we need material, he turned it on. And then when it's full, he turned it off. Obviously, that should be automated as well. So all this material handling system should be automatized. There's several ways to do it. If you go with dry, completely dry, pre-mixed admixtures, you can do it with silos like this, and continuous mixers. The only thing is that it's very difficult to get recycled materials into these types of mixtures, because as we'll come to, no, that will be later, sorry. None of the concretes with recycled materials is yet standardized, so you won't find a standard for recycled materials in concrete, which is a huge problem if you want to use them, obviously. Hopefully there's something in the future there. And then, how did we get it permitted? Actually, it wasn't that difficult. So what you need for permission in Denmark, I don't know if it's the same in Sweden, it's you need an engineering company to sign off. You need their insurance to be convinced that it's actually doable. And then you need, obviously, to have the kommune, what's it called, the city council, approve. And then after it's done, they will send a representative, and they will do some measurements in terms of vibrations and so on. And if you pass all those tests, you have a permission and you can use it. And we really we haven't done the last test, but we are quite sure we get it because we have the building, we have the site for 10 years, so we really want to rent it out to not lose a lot of money more on this project. And that's obviously like the short-term solution is, as I mentioned before, the only way we could actually get a permission was to have a static system that was conventional. So that's why we did these columns. It means the entire roof structure, the entire static system of the house is based on these columns, and the wall is actually just like a climate fence and insulation. So it means that actually the load-bearing capabilities of the walls doesn't really matter in our case. It's only the columns here, and obviously they need to converse. You'll see a lot of this around the world. I don't know what you can call it. We called it snake printing, which could be anything. Where you see like you make an outer and an inner wall, and then you make like this pattern here. In Denmark, it's not very doable because if you don't have insulation on one side or the other, you will have a thermal bridge, which is just not allowable. You can't get a permit if you have thermal bridges. So that's why we needed the inner wall and the outer wall to be completely separate. You can do this, but then you will get a really broad wall. You'll get because you would need insulation. In Denmark, you need a lot of insulation, maybe 25, 30 centimeters of insulation. And then you need this, so you will have walls of this thickness if you're printing. So obviously you will, it's not very optimal for space utilization. Obviously in the long term, more controlled mixtures, more statistics of materials, standardized materials, and so on. But that will take years and years to accomplish. So right now, we take the quick road, because this is simply too slow, because we need the European Commission to accept new standards and so on. And for those of you who've worked in that system, it's slow, really slow. So, but fortunately, you can circumvent it that way. And surface quality. That's a thing you'll always see around. It's a thing we're working a lot with right now. After we have printed, we have obviously been doing a lot of development since. The thing is that depending on your admixture, you'll see most of the, if you just go a bit front, you'll see most of the printing done around with concrete. Is where you have just a round nozzle that extrudes, and you'll have the surface of as you can see here, and that's the surface. That's what you see. A lot of architects like it. It's actually beautiful in many applications. What we want is actually to be able to control it. So right now this is what we could do. So we had short wings, as you can see here, who controls the size. So we get a square instead of a cylinder shape. But in the long term, we want to. We are experimenting right now with prolonging the wings here, so we get a completely straight, completely smooth wall. It's a bit more difficult than that, and it will take some time more. But I believe we can get there quite soon. And then Yeah. So also we are thinking about modular design. This is what we believe is our next generation of printer. In this format, we are staying to the exactly same principle, just in a modular way, so we can build it the size we need it for the project we need it for. And just to be clear, we want to be technology providers. We are a company. We don't want to go out and print houses everywhere. It's not. We are not construction guys. We want to build those machines, and then we want to teach people how to use them, and then we want to go back to Copenhagen and develop a new machine. But we are quite sure that definitely the next couple of years, so maybe in the next 3-4 years, we will have to go out there and do projects, because no one will adopt a technology that does this, like no one. Because it's way too risky. If we actually asked NTC in the beginning of the project before we started. NTC is Swedish, right? So you guys know it, yeah. If they wanted to be part of the project, and they were like, no, it's way too risky for them. So if you go to the normal construction business, they will just say no, way too risky. But they were really helpful, and they did a lot of technical advisory and so on. But they were completely out of the picture in the process, you can say. So obviously the printer needs to be much better, and at some point we hope we can make them good enough so we can put them out there and people can use them to print. Obviously we hope for construction companies can use them to print their own houses. You can see small and big ones and so on. And yeah, that's actually it. I hope we have time for, I don't know, how are we on time?
Well, we're left after time, but we will have one question, and David, where are you? There. You can come up. And during the time we switch speakers, we have one question, and we will have more questions in the plenary discussion later, so that's all right. Yeah.
I'll just switch the screen to.
Thank you. So my question is about energy consumption.
Yeah.
Does a 3D printer need a lot of energy, and is it today possible to use renewable energy?
To use what?
Renewable energy, like wind energy, solar energy. Or
for the energy consumption in the printing itself is actually not that. It doesn't use that much energy. It's actually we didn't measure it, but it's not very much. It's some, yeah. I think the energy consumption within this is the production of the material. So for instance, cement. It's high. The high CO2 footprint of cement is not like for using it; it's actually for producing it. So there you get your like, yeah. For green energy, I think no matter what you do, you can't really know for sure that you're using green energy. You're using some energy, and some energy of that will be green. And obviously, you can say you buy green energy, but in real time, you really never know. So it just comes from the grid. So whatever energy is in the grid, you will use that. But I think that's the same for everything else.